All right, welcome everybody to 21.3. This is a continuation of electrochemistry. So far in 21.1, we have looked at how to balance redox reactions, or at least you reviewed how to balance redox reactions. We reviewed what redox is. It stands for reduction and oxidation. That redox is really the focus of transfer of electrons, so from one species to another species. We looked at the acronym OIL-RIG. OIL stands for oxidation is loss of electrons. RIG is reduction is gain of electrons. And then in 21.2, we looked at voltaic cells, what voltaic cells are, how to represent voltaic cells, both in the notation and in a diagram. So a drawing and then just using the chemical species or chemical formulas to show what's going on in a full redox reaction. So now we're looking at how to evaluate a quantitative value for the amount of electrical work that can be done by a spontaneous reaction. Specifically, we're going to look at the volts, or the amount of energy per coulomb, or you can think of it as the amount of energy per charge that can be generated by a spontaneous reaction. Voltaic cells only look at spontaneous reactions and how to take advantage of that spontaneous flow of electrons to do some type of useful work for us. You can think of us as the surroundings and then the reaction as the system. All right, so the focus of 21.3 is cell potential. This is the output of a voltaic cell. For a spontaneous reaction, we know any spontaneous reaction has a delta G that is negative. However, for cell potential is positive for a spontaneous reaction. So remember from chapter 20 that entropy of the universe is positive for a spontaneous reaction. Free energy is negative for a spontaneous reaction. And then in this case, E cell, which is cell potential, is positive for a spontaneous reaction. All right, so the unit that we're going to be using to quantify the spontaneity, or how spontaneous a reaction is, or how much cell potential a reaction has, is the volt. So volt stands for our cell potential, and it can be broken down into joules per coulomb. Joules should be pretty familiar to you. It is a unit of energy. Coulomb will break down a little bit further in this unit. Okay, so when we're looking at cell potential, in the back of your book in Appendix D, there is a chart that you'll be using for your homework. That's kind of a weird looking D. Okay, D. For your homework, and a chart that you're going to be using for calculations that we do in class as well. So this is how to understand that chart. Let's zoom in a little bit. All right, it's called standard electrode potential, sometimes referred to standard reduction potential, but I think the more correct way to refer to it is standard electrode potential. So it's looking at electrodes. Remember, in any redox reaction, you have an anode. So you have an anode and a cathode, and those have electrodes that are involved in the reduction and oxidation, or in this order, in the oxidation and reduction half reactions. So what we're looking at in this chart is half reactions. So these are individual half reactions that can take place, and they're all in this chart at 25 degrees Celsius. And since they are also at standard state, that means if you have a gas, you have 1 atmosphere of the gas. If you have an aqueous solution, it is 1 molar solution, 1 molar concentration, and then all solids and liquids are said to be pure. So that's what standard again means. Notice the values here, not all charts do this, but the values here range from the highest positive and then to the greatest negative. There are arrows on either side. I don't know if this is actually shown in the back of your book, but it's definitely shown in the chapter that the stronger oxidizing agents are the ones with the higher positive values, and the stronger reducing agents are the ones with the greater negative values. What else do you need to know about this chart? All of the half reactions are written in the reducing direction. So if you remember, reduction is gain of electrons. That means all the electrons are on the reactant side of the half reaction. So you won't see electrons over here. If you saw electrons on the right-hand side, that would represent an oxidation half reaction. So all standard electrode potentials are written by convention in their reducing direction. So you'll always have them added to electrons. Okay, this E right here stands for your cell potential at standard state. So this is the same thing as E cell. Sometimes it's called E reduction, sometimes it's called E half cell. Really the E just stands for, okay, how many volts represent the potential of this half cell. Where do these numbers come from though? These numbers are really, these half reactions are compared to the reduction potential of hydrogen. This is what's called your reference electrode. So 2 hydrogen ions, this is an acid, right? H+ ions, plus 2 electrons to make hydrogen gas is said by convention to have a standard reduction potential of 0. So it's basically just our reference point. We're saying if we're comparing everything to hydrogen, how does everything compare to hydrogen? So if you compare fluorine, so the reduction of fluorine gas to fluorine in an aqueous solution, and I think this is actually not showing the negative that's right here. It's just hard to see. But if I compare fluorine half reaction to hydrogen half reaction, essentially if I put these two half reactions together to make an overall whole reaction, redox reaction, the difference between the two is 2.87. 2.87 compared to 0. Okay, so it's just telling you how likely they are to be reduced compared to each other. So as you're looking at this chart, the ones on the top, the ones with the higher positive, are more likely to be reduced or more likely to be the cathode. So cathodes are more likely at the top, or the ones with the more positive value. The anodes are the one more likely, or the ones at the bottom are more likely to be your anode. So if you took the half reaction of fluorine with this peroxide and put them together, and you ask yourself which one is more likely to be the cathode, the one with the higher positive value is always going to be the cathode, and the one with the lesser positive or more negative value is going to be the anode if you want a spontaneous reaction. So that's a lot of information, so let's summarize some of it. Put some notes at the bottom. So all of these half reactions are written in reducing direction. All right, number 2, more positive E cell or cell potential will be the cathode. And this is only, of course, for a spontaneous reaction because we're looking at voltaic cells. All right, that's the most important information from this table. Let's move on to our next slide. So how do we actually use that information and calculate? When we're doing some of these examples, you may have to reference that table without me actually going back to it. Just so you know, I would have your book available to you or that previous page open as well, so you can see some of the reduction potentials or the electrode potentials. Okay, so how do I calculate standard cell potential for a reaction? For a total reaction, so that means you have two half reactions and you put them together. The way that you do that is you take whichever one is the cathode or whichever one has the higher positive value, and you subtract from it the cell potential for the anode or whichever one has the more negative or lesser positive value. That gives you the overall cell potential for a total overall reaction. So let's apply that. So for example, let's keep our zinc and copper half reactions in our mind like we did in our previous notes. So the zinc half reaction, of course, written in the reducing direction, is zinc 2 plus 2 electrons give you zinc solid. So the half cell potential for that reaction is negative 0.76. That negative just tells you that it's less likely to be reduced. So zinc doesn't really like to grab these electrons. You can think of it as it's less likely, or it's less electronegative. It's not pulling the electrons as close to us. That's technically, when you're looking at electronegativity, you're looking at which of the atoms would like electrons in a bond, but it's still helpful to understand why zinc would or would not want these electrons by thinking about electronegativity. So it's not pulling on these electrons so much, it's less likely to be reduced. Anything with a negative value means it's definitely less likely to be reduced as compared to hydrogen. Anything with a positive value is more likely to be reduced compared to hydrogen. So all of these are compared to hydrogen. So copper, written in the reducing direction, has a positive value. So remember, the one with the more positive is more likely to be reduced or be the cathode, and the one with a greater negative is more likely to be the anode. So in order to calculate the standard cell potential for a spontaneous reaction, you have to do the following. So first, we want to determine what our cathode and anode are by looking at the standard reduction potential chart, or just looking at the values that are given, which are right here. So take a moment to determine which one is going to be your cathode and which one will be your anode. You can pause the video here. All right, so the one with the more positive is going to be your cathode if you want to create a spontaneous reaction. The one with the more negative is going to be your anode. Okay, so we did that. Next, I want to set up the balanced equation in the spontaneous direction. What that means is that the one that's going to be oxidized, I'm going to flip that half reaction. Okay, so which one's going to be oxidized? Well, I know anox. Okay, so the anode is oxidized. Red cat, the cathode is going to be reduced. So basically, I want to take this one right here and flip it. All right, let's do that. That would give me zinc solid, zinc 2 plus 2 electrons. Okay, I don't actually need to do anything with this value. I leave it. So whenever you're flipping reactions in chapter 21, you do not need to change the sign of the reduction potential. You just leave it as is. Okay, but now I have the half reaction written in the correct direction. All right, so to set up the full overall balanced reaction, I am going to add these together. Add the reactions together, I should say. Notice that what should happen is your electrons cancel. They should be on opposite sides, which means one species gave away the electrons and the other one added or took the electrons. So when you're putting this together, you should get zinc solid plus copper 2 plus makes zinc 2 plus copper solid. So the electrons should not show up in your overall balanced reaction. Okay, So I have number 2 done. Number 3, plug standard electrode potentials into equation 21.3. So this is my equation 21.3. So E cell is equal to E cathode minus E anode. My cathode right here is positive 0.34. So 0.34 volts minus, okay, and then my anode is negative 0.76. So you keep that negative there. Negative 0.76 volts. 1.10 should be your final answer. It should be positive if it is a spontaneous reaction. This is a voltaic cell, so the whole focus of 21.3 is voltaic cells. So I should be getting positive E cell or cell potential values, which tells you I did plug these in the correct direction. So if you had switched these two values, you put them in opposite places, you would have gotten negative 1.10, which would have told you, okay, you flipped them. You put the cathode where the anode is and the anode where the cathode is. So that's a good check for you moving forward. If you end up getting negative values for a voltaic cell, then that tells you, okay, flip those values, invert them. All right, so take a second to look at example question 1 and 2. You can pause here, and then when you are done, check your answers. All right, on to section 21.4, free energy and electrical work. So to review what free energy is, it is the maximum amount of useful work in a spontaneous reaction. So it's the maximum amount of work that can be done by the system. All right, so that means that for a spontaneous reaction, I want to make this bigger. Here, okay. For a spontaneous reaction, E cell has to be greater than 0. Delta G has to be less than 0. So essentially, delta G is proportional to negative E cell, right? They're opposites of each other, opposite signs of each other. Okay, so how does that relate to work? We know that the maximum amount of work that can be done by a system for a spontaneous reaction is equal to the change in free energy, which now we know is essentially equal to negative E cell times a proportionality constant, which in this case is charge. So we're looking at flow of electrons. So the total amount of work that can be done is equal to negative E cell times the charge. All right, which is summarized right here. So we are relating free energy to cell potential and electrons themselves, which have a charge. All right, so work done by the system on the surroundings is always going to be negative. So whenever we talk about work being done, that is a negative value. Okay, what is charge though? Charge is equal to the moles of electrons that are being transferred in a reaction. So it could be 1 mole of electrons, it could be 2. You know that by looking at the balanced reaction or looking at the 2 balanced half reactions, and there should be the same amount of electrons on either side. That essentially tells you how many electrons are being transferred. So moles of electrons times the charge that is present per mole of electrons. Okay, what is that equal to? That relates to a constant called Faraday's constant. Charge is equal to, therefore, N, which is moles of electrons, times a constant, which is 96,485 coulombs. Coulombs is another unit or measurement for charge per moles of electrons. All right, this is a new constant that we have not used before, and we're going to be using it for our future calculations. We're likely not going to use this equation to calculate charge by itself. We're going to input it into some new equations so we could use it to calculate things like free energy, etc. Okay, so let's move this up. There is a kind of a simpler way to write Faraday's constant, and it's like this, 9.65 times 10 to the 4, instead of writing each one of these numbers out, joules per moles of electrons, instead of using coulomb per moles of electrons. The reason is because if we can relate everything to joules and volts, which are the standard units to use for cell potential, then it's much easier to understand what we're working with and what our cell potential or what our free energy is. So since 1 volt is equal to a joule per coulomb and 1 coulomb is equal to a joule per volt, we can essentially substitute joule per volt in for a coulomb. So that's why we end up with joule per volt times mole of electron. So you're not going to really be using these units very much anymore. All right. So how do I relate this relationship to delta G? Well, I already know that delta G is equal to negative E cell times charge. And since I know charge is equal to NF, I can basically take that NF and plug it in here. So what I end up with is delta G is equal to negative E cell times NF, or this. Delta G in this case at standard state would be delta G naught equal to negative, that negative comes from here, times N, moles of electrons, times F, Faraday's constant, times the cell potential. So it's the same equation to find delta G not at standard state. Remember, you can use this equation at standard or not at standard state. All right, let's continue on. Zoom in here. Other free energy equations and how they relate to electrical potential. All right, so comparing free energy and our equilibrium constant. So how we're really looking at how the equilibrium constant now is going to start relating to cell potential. So we know that delta G is equal to negative RT ln K. That is from chapter 20. R is that universal gas constant times temperature times the natural log of K, which is your equilibrium constant. So instead of keeping this delta G, I'm going to plug in my new value for delta G. That was my equation on the previous page, which as a reminder was delta G naught equals negative NF E naught. So I'm basically plugging this in here. I end up then with negative NFE at standard state is equal to negative RT natural log of K. To get cell potential by itself, I'm just going to take this negative NF and divide it over to the right-hand side. So I end up with E cell or cell potential at standard state is equal to RT divided by NF times the natural log of K. And because I would like to make this even simpler than is shown above, if you multiply by 2.303, that essentially converts your natural log to log base 10. And then I can plug in all these constants. So R is a constant, right? F is a constant. And if everything is at 298K, then I can plug in temperature as a constant. So it gives me an even simpler expression, which is E cell or cell potential at standard state is equal to 0.0592 volts over N, which is moles of electrons, times log base 10 of K. So in this scenario, all you have to plug in is moles of electrons and your K, or your equilibrium constant. You don't have to worry about the R, the T, or the F. So it does a lot of the work for you. So let's use this in example question 1. Calculate K and delta G at 298.15 K, and this K is your temperature, for the reaction that is lead plus 2 silver ions make lead 2 plus and 2 silver solid. Go ahead and write down which equation or equations you think are most applicable, and then we will walk through it together. So you can pause here. Okay, for this equation in this problem, it looks like we might use a couple of different equations. So to solve for delta G naught, we know delta G naught is equal to negative NF E cell at standard state. We also know that we have E cell at standard state is equal to 0.0592, this is volts, over N times the log of K. All right, so what we want to solve for is K, that is right here, and we want to solve for delta G, which is right here. Now we don't actually have E cell, but directly given to us in the problem. But if I look at my equation sheet, I know that E cell at standard state is equal to E cathode minus E anode. So what I'll need to do is look at the standard reduction potentials for lead 2 and for silver ion. First, let's just identify what our cathode and our anode are without looking at those values. So lead goes from an oxidation number of 0 to an oxidation number of +2. And then silver goes from an oxidation number of +1 to an oxidation number of 0. All right, so since silver is getting less positive, it is reduced. And lead is getting more positive, it is being oxidized. So that is our anode. The one that is undergoing oxidation is our anode, and then our cathode is the one being reduced. Okay, so let's go ahead and look up, our cathode. Let's change this to black there. So our cathode, I know, is our silver half reaction. So that's silver plus going to silver. If you look up that value in the back of your book, you should get 0.80, or I think it's on the chart a few pages before this. And then if you look up your standard reduction potential for your anode, which is lead, that is negative 0.13. You might see 0.125 or something like that, but you're just going to be tested on the values that are given to you for the exam. So you should all have the same values for the exam. All right, so when we plug this in, I would end up with 0.80 volts minus negative 0.13 volts, which would give you 0.93 volts. It's a positive number, so that means I did plug these in the correct direction to get a spontaneous reaction. All right, but I can't change the reaction anyway because it's written as is. All it tells me is to calculate delta G and K, not to assume that it's a voltaic or an electrolytic cell. All right, so let's move on. So I can use that E cell value right here and plug it in here and plug it in here to solve for K and to solve for delta G. So let's start with, ooh, I didn't mean to do that. Let's get rid of that. Okay, so there, little dots. So delta G naught is equal to negative NF E cell. So I know delta G naught is equal to negative NF times 0.93 volts. Faraday's constant is 96,485. I'm just going to use the whole constant here. Coulombs per mole of electrons. So plugging that in, that tells me that delta G naught is equal to negative N times 96,485 coulombs per mole electrons times 0.93 volts. So last but not least is finding what N is. The best way to find what N is to look at the two half reactions independently, in my opinion. But you might also be able to see that overall the number of electrons that are being transferred is 2. But let me just prove that to you. So you have your two half reactions. You have silver. If you look at the standard electrode potential chart, you'll see this half reaction. You'll see silver plus 1 electron gives you silver solid. Okay, so that's the half reaction you're looking at. And then for lead, you'll see lead 2 plus 2 electrons gives you lead solid. All right, so in order for this reaction, total reaction, to make sense, what you would first need to do is flip your oxidation half reaction, which would be this one. So I want to flip that. You end up with lead solid, gives you lead 2 plus 2 electrons. And for this one, you would need to multiply it by 2 because you need the same number of electrons on each side. So that does not affect your standard electrode potentials. If you flip or multiply it, you're still going to end up with the same electrode potentials. plus 2 electrons gives you 2 Ag solid. All right, so 2 electrons are on opposite sides of the arrows. One's on the reactant, one's on the products. Okay, so then when you add it together, obviously you get the overall reaction. So I'm not concerned about that right now. What I'm looking at is the number of electrons that were transferred, and it's 2. So the number that you need to cancel out on each side, that's the number that goes in for in. So if I want to simplify this even more, or I should say solve for it even more, I have negative 2 moles of electrons times 96,485 coulombs per mole of electrons. Let's make that a little smaller. And then that is times 0.93 volts. If you want to check your answer first and then come back, that's great. Volts let's see. Oh, okay. This is what I did. I'm going to back up right here. Okay, so as a reminder, volt is equal to a joule per coulomb. So it's the same thing right here to put 0.93 joules over coulomb. So then you can see more easily how these units cancel. So coulomb and coulomb, moles of E and moles of E. So you end up with, for your final answer, negative, let's move it over even more, you end up with negative 1.8 times 10 to the 5 joules, or you could say negative 0.18 times 10 squared kilojoules. Either one of those is appropriate. All right, so we'll move on to finding K. All right, so we have this equation up here. It says that E cell at standard state is equal to 0.0592 volts over N times log of K. So let's rewrite that down here. We want to solve for K by itself. Volt over N log of K. So what we can do is divide over 0.0592 volts and multiply N over. So we end up with E cell times N divided by 0.0592 volts is equal to log K. To get rid of that log, you're going to do base 10 to each side. So you end up with K is equal to 10 to the E cell times N over 0.0592 volts. Now, remember in we have 2 moles of electrons, and that K is a unitless value. So go ahead and evaluate that. Pause the video and then check back for the correct answer. Okay, your final answer should be 2.6 times 10 to the 31, 2 sig figs because there were 2 sig figs here for E cell not. This 2 is an exact number, so it does not decrease the amount of sig figs in your final answer. All right, on to our next slide. All right, here we take into consideration concentration and how it affects cell potential. So far we've only looked at cell potential at standard state. I don't know why that's not zooming in. Okay, at standard state, but we're going to look at how to calculate things like delta G or E cell not at standard state. So remember that if I want to calculate delta G not at standard state, I need the standard state value for delta G, and then I need to add RT natural log of Q. So if I substitute in our new expression for delta G, which is negative NF E cell, I get negative NF E cell not at standard state is equal to negative NF E cell at standard state plus RT natural log of Q. If I divide both sides by negative NF, so all of the expressions by NF, what I get is the following equation called the Nernst equation. All right, E cell, so cell potential at any point of the reaction, is equal to E cell at standard state minus 0.0592 volts divided by N times log of Q. Remember, Q is your product concentration over the reactant concentration raised to the correct exponents. So a really interesting thing about this Q, though, is it's not QC or QP, or it's just looking at products over reactants. So you can actually input both units of molarity and atmospheres simultaneously. You do not have to convert one into the other. So that's pretty great. No conversion necessary. So let's use this equation to calculate E cell for the following. I think it should be voltaic cell. Yeah, it is a voltaic cell. Okay, so what you have on the left-hand side before this double line is the anode. Right here is our anode. And then on the right-hand side, we have our cathode. So something new here, we have platinum, which is an inactive electrode. Just means that it's not actually participating in the redox reaction. So it's there as a conduit or as a pass-through for electrons, but it's not being oxidized or reduced. What's being oxidized and reduced, or in this case what's being reduced, is the hydrogen ion, and it's being reduced into hydrogen gas. Okay, so the first thing that we should do is write out the equation that we're going to be using to solve for E cell. Let's do black. So E cell not at standard state means we need E cell at standard state minus 0.0592 volt over N times log of Q. The first and easiest thing to find would be E cell at standard state. If you remember, E cell at standard state is equal to E cathode minus E anode. So what you want to do is look at your standard electrode potentials for cathode, standard electrode potentials for the anode, these two half reactions. So if you're like, I don't really know what the half reactions are based on what I have in front of me, let's write those out. Let's start with the cathode. It's actually easier if you just find where hydrogen is on the standard reduction potential chart, and then it'll show it for you. So what you should see is 2H plus 2 electrons makes H2 gas. It should give you an E cell value of 0 volts. For the anode, what you should find is zinc 2 plus 2 electrons gives zinc solid, and that the E cell for that is negative 0.76 volts. Okay, so let's calculate E cell by taking 0 volts minus negative 0.76 volts. So I'm just plugging in my cathode here and my anode cell potential here. So you should get a positive number, which means it's a spontaneous reaction of 0.76 volts. So now I have what I've highlighted, and that is E cell at standard state. All right, let's move on to what N is. What is N? N is moles of electrons in the overall balanced reaction. This one is rather easy because both of these half reactions have 2 electrons. And really, that tells you that the number of electrons that are being transferred is 2. But in order to see that more fully, what I'm going to do is just erase these values and put these two half reactions together. So remember, my anode has to be flipped so that it's showing in the oxidizing direction in order for my two half reactions to add together. So an oxidizing half reaction means electrons are shown on the right. So when I add them together, the two electrons end up canceling. So my final balanced reaction is 2H plus zinc goes to zinc 2 plus H2 gas. So N then is 2 moles of electrons. That's how many moles of electrons are being transferred. Let's highlight that. Okay, so the last thing that I don't have is Q. There's a couple ways to do Q. Oh, shoot. Don't want to do that. A couple ways to do Q. Let's kind of raise this up a little bit. And I would say to look at the overall reaction that we just balanced right here. So let's write our Q expression for that reaction. It would be pressure of H2, since it's a gas, times concentration of zinc 2 plus over the concentration of H plus squared times 1 because we have zinc solid. Okay, that 1 stands for zinc solid. All right, so let's plug in the values that we see up top. So what about pressure for H2? That's 0.30. So I get 0.30 times the concentration for zinc 2 plus, which is 0.010. Let's put little parentheses around that. Divided by the concentration of H plus, which is 2.5. And that's squared. All right, you can pause here to evaluate Q and then check your answer. Your answer should round to 0.86. There should be 2 sig figs in your final answer. Because that E cell is greater than E cell at standard state, so E cell is greater than E cell at standard state, that just means it's more spontaneous than if it were at standard state and everything had an atmosphere of 1 or a molarity of 1 or is a pure solid or liquid. Okay, so, and I promise this is the answer. If you're like, I didn't get that, I guarantee you there's something that you input wrong into your calculator. So go ahead and check that. All right, on to the next slide. Okay, so what happens as concentrations start to change? So think of or look back at that previous example that we did, and let's pretend that the concentration of zinc 2 plus is now 0.015 molar, and that the concentration of H plus is now, let's say 2.0 molar, and then the pressure of H2 is, let's see, that would increase 0.40 atmosphere. Okay, so what is, in this case it wouldn't be QC, it would just be Q. What does Q equal in that instance? If you need a reminder, again, go back to that balanced equation that we just looked at and then see what the products and the reactants are. But we are plugging in pressure of H2 times the concentration of zinc 2 plus over the concentration of H plus squared. So let's plug that in. We have 0.40 times 0.015 all over 2.0 squared. Okay, so we're going to calculate that, pause, and then come back to check your answer. All right, you should get a Q that is much larger than your previous Q because you have more products, so 0.0015. So let's plug that back into E cell. So calculate for our new E cell. We're trying to see what happens to our cell potential as we gain more products and lose the reactants. All right, so go ahead and evaluate that. Give yourselves a minute and then check back for the answer. All right, so you should get 0.84 volts. If you remember on the previous page, E cell was equal to 0.86 volts. So what's happening is spontaneity is decreasing. As the products go up, or as products increase, the reaction is getting closer to equilibrium. So, less spontaneous. So E cell is decreasing. So you should know that since at equilibrium, delta G is 0, that also means E cell is 0. There is no spontaneity left. It's dead. The battery is dead. It's going nowhere. So it's spontaneous in neither direction. Okay, here's a visual of what is happening during a cell operation or as a battery is working. So at the very beginning, how batteries are made is that the cell potential would be much greater than even the cell potential at standard state. So it's very spontaneous, right? The electrons are moving from the anode to the cathode. Here's my little salt bridge that just allows for the ions to transfer into the electrolyte solutions to balance out the charges. For copper, since it's being oxidized, solid copper is losing electrons and then going into solution. Since silver in this case is being reduced, it's gaining the electrons that are coming in here, and it is plating onto this silver. So you would start to see this silver metal kind of build up and get thicker, and this copper gets skinnier and skinnier. Then as the cell or the battery continues to operate, you move to a place in which E cell is equal to E cell at standard state. So this just means you're currently at standard state. When your E cell is less than E cell at standard state, that means you're just less spontaneous, so you're losing spontaneity. When E cell is equal to 0, that means that your battery is dead. Nothing's happening. So that means there is no longer any transfer of electrons. They aren't going anywhere. There's no more change in the thickness of the metals occurring, no more ions really transferring into the electrolyte solution, and it's done. It's going nowhere. Okay, for our last page for 21.4, I think this is, right? Yeah, 21.4, we're going to look at concentration cells. Concentration cells are those that use the same substances but just at different concentrations. For example, we're going to use a pH meter. So how does your pH meter work? It uses a concentration cell. On one side, you have H plus ion, and the other side, you have H2 or gas. So let's draw a little diagram of your pH meter. So the little probe, looks like this, and there's kind of these wires in this little tube inside. Okay, and this is your pH probe. Okay, inside the inner tube, this is the standard H or hydrogen electrode. And actually, let me clarify. I think I misspoke in saying on one side there's H plus, on the other side is H2. On both sides there's H plus and H2, but at different concentrations. Okay, so in the inside of this tube, the hydrogen half cell or the hydrogen electrode is at standard state. So it has 1 atmosphere of the H2 gas and it has 1 molar concentration of the H plus solution. On the outside is a membrane that allows a flow of H plus ions. And that is also the place, I'll just keep the same color, that oxidation is occurring. So it allows for H plus from your solution. So you can kind of think of it as, you have your solution here, it's in a beaker, and the H plus ions are allowed to flow in here to detect essentially how much of the H plus is in your solution. So this is how the pH meter is actually calculating your the pH of your solution. So it takes the first half reaction, which is H2 gas at 1 atmosphere. Remember, it's standard. And 2H plus aqueous, and we don't know the concentration, it's unknown. You can think of this as from your beaker, plus 2 electrons. Okay, this is the anode. And then in the cathode, we have 2H plus aqueous at 1 molar, plus 2 electrons, make H2 gas 1 atmosphere. So if you take those two half reactions, and this one I didn't write down, but this is the cathode. So if you take those two reactions and add them together, what you end up with is 2H plus aqueous 1 molar makes 2H plus aqueous unknown. Why is that? Because the gases end up canceling because they're at the exact same concentration, and then the electrons end up canceling. So all you have is H plus aqueous, one is at 1 molar and one's an unknown concentration. Okay, and I'm kind of running out of room. Let me kind of squeeze this down a little bit. All right, that's a little bit better. So let's write out what our E cell would be for this reaction. If we wanted to calculate what the cell potential was, E cell is equal to E cell naught minus 0.0592. This is the Nernst equation, times log of Q. Q would be the concentration of H plus squared over the concentration of H plus squared. This would be the unknown concentration, and this would be the standard concentration. This number right here would be 0. This number right here would be 1 molar. Okay, so even though we're not going to solve this complete thing, you can see a couple things. We have this number, we have N, and we have 1 molar. If we can use the pH meter to basically tell us what our cell potential is, it is technically a voltmeter. So it's reading cell potential as it's converting it and then giving you a pH reading from that. So it's reading the potential difference between the unknown solution and the standard solution inside. And from that, what it can do is use this calculation to solve for our one unknown. Notice if you have H plus concentration, then you can calculate your pH because pH is equal to negative log of the H plus concentration. So your pH probe really is just a voltmeter. It reads the cell potential between your solution and the standard inside. All right, let's finish off with these questions. So can a concentration cell be a voltaic cell? Meaning, can it be spontaneous? So the answer is yes, it can be spontaneous. You just have to make sure that the concentrations are different from each other. So yes, it can be. If the concentrations between the two species were the same, that means there's no change that's going to occur. There's no transfer of electrons because neither one of them has a greater potential than the other since they have the same products and the same amount of each product in there. So concentrations just need to be different. Okay, let's see. At which stage or stages in a cell operation is there no spontaneous movement of electrons? So think equilibrium. That stage is when E cell is equal to 0. So when there's no cell potential, that means there's no spontaneous movement of electrons. All right, that is it for this section. I will see you next time.